Okay, welcome back. This is Math 1610. I'm trying to get this thing to the side here. 4.4 concavity in the second derivative. So we looked at the first derivative, and that told us where functions are increasing, decreasing, or staying constant. And then from that, we could determine whether or not there was a max or a min there. So this is just carrying on, and you could look at the third derivative, the fourth derivative, fifth derivative, and as a matter of fact, when we build approximations to functions, that's exactly what we do. We want to align all the derivatives with, it's like an alignment of the derivatives of a polynomial with the derivatives of a function, and that way you could build a polynomial that kind of mimics the behavior of a function. Okay, but that's not here nor there. Let's just focus in on what the book is demanding of us right now, right? So, so 4.4 concavity in the second derivative. First off, we're going to have some definitions. Okay. So the definition of concave up. This is just a happy face parabola. Okay, so it looks like this. And if you look at the second derivative of a parabola, so if you have f of x equals x squared minus 9, f prime of x will be 2x. And then f double prime of x will just be 2, positive. And that will be kind of the determining characteristic on whether or not it's concave up. So if the second derivative of x is greater than 0, it'll be concave up. And here we have our second derivative is greater than 0. So how did that relate to your pre-algebra work? So it's always good to kind of try to link things together, right? If you remember, the parabola of the form y equals ax squared plus bx plus c, if a was greater than 0, you would have a happy face. And then if a was less than 0, you'd have a sad face, okay? And it's basically the same kind of spiel here. If your second derivative is greater than 0, it's a happy face. If your second derivative is less than 0, it's a sad face. Okay, so concave up now or concave down. So here we have a sad face. So like if you had a parabola with a negative leading coefficient and you took its derivative twice, you would see that the second derivative would be less than 0. In other words, it's a sad face, right? So, and that's exactly what we have. In physics, the second derivative is basically the rate of change of the rate of change. It's the rate of change of your speed, right? You're either accelerating or you're decelerating. If it's concave up, you're accelerating. In other words, your slope, which represents speed, is increasing. And geometrically, what that looks like, well, that just means the slope values. So if you have here, maybe the slope is -5. Here, maybe the slope is -1. And you see that as the slope values go around here, they're increasing. Okay, the rate of change of the rate of change is increasing. And geometrically, what happens then, it kind of traces out that happy face shape, right? And the same thing for down here. This is deceleration. So the slopes values go start at 5 and then go down to the speed of the slope. You can kind of think of those as kind of the same thing. It's decreasing. It's decelerating, you know. And geometrically, what happens with that tangent line as it's decelerating, it's kind of tracing out the sad face figure. Okay, so that's the spiel, I guess. My introduction to it. Let's look at then this theorem, which is basically, I've already kind of let the cat out of the bag. Okay, so the test for concavity, and the book gives it as a high-powered theorem. So theorem 4.7. We have to have the existence of a derivative on maybe some open intervals. So let f be a function whose second derivative exists on an open interval I. Okay, because what we're going to end up doing is kind of the same type of analysis that we did with the first derivative. We're going to do a number line and look for the test value, sign, conclusion, all that great stuff. Okay, so anyways, if you have the second derivative being greater than 0, then you have happy face, right, or concave up. If you have the second derivative being less than 0, then you have a sad face, concave down. Okay. Okay, so let's do one of these. Let's actually see if we can accomplish this. So look at an example. We have f of x equals e to the negative x squared all over 2. Okay, so a function like this may be used for probability. It's a bell-shaped curve. Okay, I don't know where it's centered, but I believe it looked like this. So in education, we always talk about the bell-shaped curve. That's one of these guys. And in probability, you figure out the area under it, and that tells you probability. Okay. So anyways, we want the derivative in our universe. We just want to get the derivative and do that. So the derivative and exponential, you just get the exponential right back. And then you have to tack on the derivative of the exponent. So that'd be negative 2x over 2. In other words, negative x. Clean it up a little. Okay. Then I'm going to need the second derivative, prime of x. So I have two parts here. I usually leave the first one alone and then take the derivative of the second. So I get e to the negative x squared right back, and then times the derivative of the exponent. And then minus, now I take the derivative of x and leave e to the negative x squared over 2 alone. Okay. Okay, so then I'm going to clean it up a little. I can factor out an e to the negative x squared over 2. And I'll be left with x squared, and it looks like minus 1. Okay. Okay, so at the end of the day, I'm setting this equal to 0. Okay. And I'm finding basically like critical points, except we're not going to call these critical points. So instead of critical points, we kind of think of these as potential inflection points. Okay, and I'll talk about inflection here really quick. So anyways, I'm setting it equal to 0, and I have two parts here. I mean, normally we look for where it's not defined as well, and those can be points of inflections. We won't have any places where the second derivative is undefined here, though. Okay. So anyways, we take the two parts and set them equal to 0. This exponential thing, you can't put anything in the exponent that's going to cause it to equal 0. That will just never happen. So we can kind of forget about that. Take x squared minus 1, set it equal to 0. Looks like we're getting plus or minus 1 for our potential inflection points, which I'll talk about here in a second. Okay. Okay. So I draw my number line just like before. I'm going to remind myself I'm working with the second derivative, because when I evaluate my test values, I'm going to be plugging them into the second derivative up here. Okay. Okay, so I label my test values. Here's negative 1, here's positive 1. All right, those are the potential inflection points. Then I need my test values, my signs, and conclusions. Okay. I'll do that in red. So x is negative 2. Okay, back to the yellow thing. This yellow, the second derivative. Okay. If you put anything in an exponential, it'll be positive. Okay. E to any power will be a positive number. Okay, so it's going to be, I can kind of forget about that exponential part and just work with the x squared minus 1. So if I put negative 2 in for x squared, I get 4. 4 minus 1 is 3. That's positive. And so I have a happy face. Let's try 0. Again, I could just forget about the exponential part and then put 0 into x squared minus 1. 0 squared is 0. Minus 1 is negative. And so that's a sad face. And then try x is 2. So 4 minus 1 is positive 3. So that's going to be a happy face. Okay. before, we could tell kind of if we had a max or a min by looking at this analysis. And here, what's happening here is there'll be these inflection points where it goes from concave up to concave down and vice versa. So we kind of zoom in on that idea just the same way we zoomed in on critical numbers in the previous section. And we're going to eventually develop a second derivative test, which will also allow us to find maxes and mins. In general, why do we even bother with the second derivative? It's about graphing. It's about figuring out the shape of a graph. Okay, is it like concave up or cup? Is it going up or concave down? Okay. So, anyways, here we go. Points of inflection. First off, the function must be defined at a point for a point of inflection to exist. So given f of x is defined, an inflection point is where the function goes from concave up to concave down or vice versa. So it goes concave down to concave up, or concave up to concave down. Okay. Okay. Then theorem 4.8 is like the relative max theorem. So if you have a relative max at C, then f prime of C will either be 0 or f prime of C will be undefined. So in this case, if C comma f of C is a point of inflection, then f double prime of C will equal 0 or it'll be undefined. In other words, when we go to make our number line, the points we're going to be looking for will be the points where the second derivative is 0 or the second derivative does not exist. Okay. Visually, points of inflection are kind of create S-shaped curves. Okay, and it may not seem like it's an inflection point, but here, right now I am concave up, believe it or not. And then it does like this S, and all of a sudden it's concave down. Look at that, it's concave down. Okay, this point right here is a point of inflection. So that's going from concave up to concave down. Okay, right here is an inflection point. Another version would be going from concave up to concave down. Okay, and there's my point of inflection. So, sorry, this is concave down to concave up. With a inflection point right there. Sometimes it'll go from concave up to concave down, but it won't be an inflection point technically, because maybe you'll have an asymptote, right? So something like this, which is concave up, and then all of a sudden it's concave down. This point here, where the asymptote is x equals c, I'll call it. There's no point to have an inflection point, right? But it is going from concave up to concave down. So just because it goes from concave up to concave down does not necessarily mean that you have an inflection point. Okay, so just be aware of that sort of mini issue. Okay, so anyways, let's try the types of homework problems you'll be looking at. So let's look at an example here. We want to find the inflection points and note the concavity. Okay, so when I look for inflection points, I'm really going to be analyzing potential inflection points. I won't really know if they're, I mean, usually I'm too busy to kind of, I'm going to plot anything that's potentially an inflection point on my number. Okay, so let me just dive right in. F of x is sine of x over 2. Okay, and we're concerned with the interval from 0 to 4 pi. Okay, so I need the second derivative. F prime of x is cosine of x over 2. times the derivative of x over 2. That's a chain rule. Okay? So this is 1/2 cosine of x over 2. And then f double prime of x is going to be 1/2 times negative sine of x over 2. Derivative of cosine is negative sine. And times the derivative of its guts, which would be 1/2. So we'll end up with negative 1/4 sine of x over 2. Okay? Okay, so once we get the second derivative, again, there's these, it's just like when you're working with the first derivative. You want to find where this thing doesn't exist. And in this case, because we're dealing with trig functions, that just doesn't happen. So no, doesn't happen. Then we also want to find where it's equal to 0. Okay? So you take negative 1/4 sine of x over 2 and set it equal to 0 and solve. In particular, on the interval from 0 to 4 pi. Okay, so I'll just remind myself of that. All right, so multiply both sides by negative 1/4 sine of x over 2 is 0. And then we're thinking about where is sine going to be equal to 0? Okay. So that'll be at 0, pi, 2 pi, 3 pi, 4 pi. So n pi, n times pi, where n is any integer, counting numbers like negative 1, negative 2, 0, 1, 2, 3, those. Okay, multiply both sides by 2, and I have 2n pi. So for n values in that set of integers, is in the set negative 3, negative 2, negative 1, 0, 1, 2, 3, etc. Okay, so dot, dot, dot in both directions. You want to basically plug these n values in for n here and get all the answers that are in the interval from 0 to the pi over 0 to 4 pi. Okay? So if you put in negative 1, that's not in the interval, right? That's negative 2 pi. So you try negative 1, or sorry, you try 0. You plug 0 in there, 0. We only want ones inside the interval. Okay, we don't want the endpoints. So I try put 1 in there. I get my first one is 2 pi, then put 2 in there, and that's 4 pi, so that's an endpoint, so we're done. Okay, so I'm going to draw my number line. I'm only worried about the interval from 0 to 4 pi, and my only potential inflection point is 2 pi. Okay, so then I need to do my test values and signs and conclusions. And I'm working with f double prime of x, which in this case is negative 1/4 sine of x over 2. Okay? So I'll be putting my test values in there. So I try x, my test value x is pi, right? Just try something in between 0 and 2 pi. You plug pi in there, you get negative 1/4 sine of pi over 2. Sine of pi over 2 is 1, so 1 times negative 1/4 is negative, so it's a sad face. Try x is 3 pi. Okay. 3 pi over 2, sine of 3 pi over 2 is negative 1. Negative 1 times negative 1/4 is positive, so it would be happy face. Okay. The function is defined at 2 pi, so there must be a point of inflection there. It's going from sad face to happy face. Point of inflection at 2 pi, comma, f of 2 pi. So f was originally sine of x over 2. So if you put 2 pi in there, you get 2 pi over 2, which is just pi. Sine of pi is 0. Okay, on my test, I usually won't ask for that point of inflection. I'll just want to see the number line and your happy faces and sad faces, okay, with your test value signs and conclusions. it's probably not a bad idea to go look at last year's test and kind of see how the layout's going to go. But anyways, let's look at an example, another example. This one's kind of weird. Y equals x minus ln x. Okay, so y prime is 1 minus the derivative of ln x is 1 over x. I'm going to rewrite that though, so it's a little bit more user-friendly. Y double prime, derivative of 1 is 0, and then I have negative, the derivative of x to negative 1, bring down the negative 1, times x to the negative 1 minus 1 is negative 2. So I'll end up with negative is positive 1 all over x squared. Okay, so again, where is the second derivative non-existing, and then where is it equal to 0? Those will be the points I put on my number line. Okay. So y double prime is 1 over x squared. Its issue then is that x equals 0. You can't have that denominator equaling 0. So there's one critical number, or in this case, one potential inflection point. Where does 1 over x squared equal 0 then? Multiply both sides by x squared. Get 1 equals 0. Never. It just does not ever equal 0. There's no solutions to that problem. So our only inflection point is going to be at 0. One other issue is this has an implicitly defined domain, because the ln of x, if you think about this picture as a picture, its domain is going to be from 0 to infinity. Okay, so the truth is we won't even include 0 on our number line. If you wish, you can draw it like this. Here is 0, and we're going from 0 to infinity. So our test values, signs, and conclusions will just work with this one interval. Okay, so the test value, we'll try x is 1, and then we're plugging it into the second derivative, which in this case is 1 over x squared. Okay, so if you plug x is 1 into that thing, you're going to get 1 over 1, which is positive. In other words, it's concave up, and it'll be concave up on its entire graph. We could take a look at the thing. Let's go to the Desmos and figure it out. Let's see, we got y equals x minus ln of x, and you can see it's just it has that U shape to it forever and ever. It's just big U shape. Looks like it has a corner, but it doesn't. It's concave up on its entire domain. Okay, so that one's kind of weird. Anyways, you can actually use the second derivative to find mins and maxes sometimes, okay? And you can kind of tell how it's going to work looking above here. If I have a critical value over top of this interval from 0 to 2 pi, so let's pretend I found the derivative, the first derivative, and there's a critical value right here at pi. Okay? If it's concave down and there's critical value at pi, that critical value is going to end up being a maximum because it's going to be at the top of this concave hill. Okay, and then likewise, if you found this other critical number was 3 pi, and it's in an interval that's concave up, that thing is going to be a minimum. Okay, so that's the whole idea right there. Let's write it out in all of its glory. Second derivative test. Okay, so this is, I think it used to be called theorem 4.9 in the book, so let's take a look at it. We'll let f be a function such that we have this f prime of c equaling 0. So we have at c a critical number, and the second derivative exists on an open interval containing c. Okay. If in the interval the second derivative is greater than 0, that will be the case where you have concave up, and therefore you'll have a min. Okay, so a relative min there. Secondly, if f double prime of x is less than 0, that will be concave down, and it's kind of like a hill, right? So you'll have a relative max. Okay. And then thirdly, if f double prime of x, and this is the crummy part, if that thing equals 0, then the test is going to fail on you, and you have to go back and use the first derivative test to figure it out. Okay, okay, so let's take a look. Look at some example from the book. So we have f of x equals x squared minus 4x cubed plus 2. Usually these polynomials will be pretty easy. So f prime of x is 2x minus 12x squared. And then f double prime of x is going to be just, what did I do wrong? Did I write it wrong? Yeah, that's x to the 4th. It's like, what is going on here? Sorry. So this will be 4x cubed. And then f double prime will be 12x squared minus 24x. Okay. I need to get the critical numbers and the potential inflection points. So I set the derivative equal to 0. Solve that. So we'll get one at 0. And then we'll get one at 3. Okay. We don't need to look for where the derivative is not defined. It's defined everywhere. And the same thing for the second derivative. That thing is defined everywhere. And I just need to set it equal to 0 and solve. Okay. And again, it looks like we're getting a 0. So x is 0 from the 12x equaling 0. And then 2 from x minus 2 equaling 0. Okay, okay, so I'm going to kind of stack my number lines. This will be f prime of x. This guy will be f double prime of x. Okay. Go ahead and put your critical values here. 0, 1, 2, 3. 0, and we have 3. I usually don't put the other tick marks in there, but I'm trying to line everything up. So this will be 0, and then 2. And then supposedly all I need to do is just look at the second derivative to get to determine whether or not we have a max or a min. There will be an issue at 0, right? And that's kind of said so in the proof. The test is going to fail if the second derivative is 0 and the first derivative is 0. And that's kind of the case we have here at 0. So I'll have to do something else there, but for the critical value at 3, I will be able to determine if that's a max or a min without having to do the increase-decrease stuff. Okay, so anyways, let's get at it. Try -1. F double prime is sitting right here in red. Okay, so -1 in there, 12 minus -1 squared is, so it'll be 12 times 1 is 12. Minus 24 times -1 is plus 24. So 12 plus 24 is a positive, so it's concave up. Try x is 1. 12, that'll be 12 minus 24 is negative, so sad face. And then try 3. So 9 times 12 minus 24 times 3. 9 times 12 is over 100, and 24 times 3 is under 100. So that'll be something big minus something smaller, which will be something positive. Oops, I started drawing it concave down. It's not. It's concave up. Okay, so we have this critical number over top an interval that's concave up. That means we have a min at this point 3. Okay? So automatically this tells us from the second derivative test we have a min at 3 comma whatever it is when you put it back in, -25. Okay. The only other question then is, what the heck is 0? Is that a max or a min? And unfortunately, you know, this is the crummy part. If the second derivative is 0 at that point, you will have to go back and do your test values, your signs, and your conclusions. Okay. But we can do that pretty quickly. X is -1. This time I'm plopping it into the blue equation. Or actually, let's use this version of it, right? That'll be a little easier to do on the brain. All right, so putting in -1, the outside is always going to be positive because it's x squared. X squared is always greater than or equal to 0. The inside, -1 minus 3 is negative. Okay, so it's decreasing. And then on the other side, let's try x is 1. 1 minus 3 is negative, so it's decreasing again. So it's neither. This thing is neither a max or a min by the first derivative test. Because if it's down, down, it's... Okay, in general, in the grand scheme of things, I'm not going to be using the second derivative test pretty much ever. It'll probably never happen. Once you get the Calc 3, there's kind of like something similar there that you do use, though. So it's important to kind of see it here and maybe gain some intuition. Okay, but yeah, I'm not going to be using the second derivative test much of ever. Okay, it's just there. Maybe next year I won't even teach it. Okay, the main important part of this section is just determining concavity. Right? The inflection points turn out not to be even that important either for me. Okay, not to say that they're not. If you study logistic curves are of this family called sigmoids, and they look like this. And right in the middle of that logistic curve is an inflection point. These things are used to model disease, the spread of disease and that sort of thing. So they have a limiting capacity up here, which could be basically like the population of the United States. So you know the people will become infected, and it'll taper off once almost everybody's infected. The rate of change will lessen. But the place where the rate of change of infections is the greatest will be at this inflection point. So it's important to note that in that context. So, you know, what I'm saying is although we're probably not going to get too much into it, I guess, it's definitely important in mathematical modeling, which I don't do enough. So I don't know. Okay, so anyways, the second derivative test, no, not that important. Okay, I'll leave it at there. Leave it at that, and we'll see you next time. Thanks for watching.